Hello, my name is Virgil Goldberg and this is my Physics Lab 5 on elastic collisions of pool balls. So as a low introduction, the aim of this experiment is going to be to compare a real life and a computer simulation of an elastic collision between two identical balls at an angle, and in this example it's going to be pool balls. So we will be comparing the results with the simulation, and we will see that the results, while very similar, surprisingly similar, are very hard to we'll say model in a perfect way, because there's always going to be outside constant and slight real life applications that cannot be reflected in simulations. So here are the physics principles that we're going to be using. So there's of course Newton's second law as usual. There's also going to be momentum principle, but more importantly the conservation of momentum, which we will see does not apply directly. There's obviously the energy principle, so the conservation of energy within a system, which also means that the inertial energy will be equal to the final energy in a system. So here are the different equations. We of course have Newton's second law as usual and the position and velocity updates. We also have the energy principles, such as that delta E will always be equal to 0 in a given system, as energy cannot be created or lost. And kinetic energy is always equal to half mv squared, of course. There's also, of course, the momentum principle in elastic collisions. So this is the momentum, we'll say, form of an elastic collision. So we see that the mass of the two first objects and their initial velocities must be equal to the, we'll say, final momentum of each component at the end of it. In an elastic collision, therefore, the initial kinetic energy will be equal to the final kinetic energy, but the final momentum will not be equal to the original momentum as it would be in an inelastic collision. So here is the experiment. As we can see, the system is those two balls. So there is an initial impact where this ball will roll here, impact it, and then as we can see here, they will go into two different paths. So when we follow their trajectory, we can see that for the leading ball, the hitting ball, there is a change in velocity after the of x direction and y velocity, and we can see that with the second ball, the hit ball, there's also obviously a change of velocity from 0 to a certain velocity. If we calculate them, we find that the initial velocity of ball 1 is this, the final velocity is this, and final velocity of the second ball is this. And if we do the math, it does satisfy this idea of this equation. It does satisfy, as we can see, because they're the same mass. This plus this is about equal to this, and this plus this is also about the same answer as this. So as we can see, it is quite similar with slight differences. Here is the code for the simulation. So of course we can see here that the definition of the objects, and here we have the initial conditions, the mass, position, velocity, and the angle of collision, which is in this case put on 90 degrees, even though it's not really 90 degrees in the real experiment. So here we have the position update and the energy calculation and how to plot this energy, as well as drawing the trail of the ball collision. So here is after the collision. We see that we have ball 1 and ball 2, so we have all the variables for the two different balls, as those will be different obviously, because one is going in the is going up in the y direction and one is going down in the y direction, and they have different x component velocities. So here's the result. As we can see, well, it's not in the same direction, but we still can find the same general trajectory. Of course, in this case, it hits at perfectly 90 degrees, which in our case wasn't the case. It wasn't perfect. And here's the energy over time. So here we have the energy of one ball, here's the energy of the second ball, and here is the total energy of the system. And as we can see, the energy remains constant throughout, showing an elastic collision. So as a conclusion, we see a slight divergence because, I mean, it is impossible to have a perfectly elastic collision. There's sound emitted, there's friction with the table, friction in the collision, which means that some energy will be lost from the system. And also the angle was obviously not perfect and was not exactly 90 degrees. So now what if we change the angle? Then the collision will still be elastic, doesn't change that, which means that the energy would be the same, and the only difference would be the xy components of velocity of the different balls, because they would be going in different directions. But what matters in the total energy and the elastic collision is simply the initial velocity and mass of the ball that's hitting the other. And now what does it mean, the difference between energy and momentum conservation? Well, in an elastic collision, there will be energy conservation. The kinetic energy is conserved, while in an elastic collision, the momentum will be conserved and there will be a loss in energy. Thank you very much.